Welcome back to another tutorial on how to find reactions using distributed loads. So we've already seen how to calculate the reactions on a simply supported beam with a uniformly distributed load, and we've also seen how to calculate the reactions on a simply supported beam with a triangular distributed load. What happens when we mix them together? Let's see. So in this example, we've got a simply supported beam, and for the first 4 meters from A to B, we've got this triangular distributed load, which goes from 0 until a height of 15 kilonewtons per meter. And then for the remaining 5 meters until point B, we've got a uniformly distributed load at that same constant level of 15 kilonewtons per meter. Let's just think back to what we discussed previously. The area under that shape is what gives us the force. So in this case, I've got this triangle of 4 meters on 15 kilonewton per meters, and I've also got this rectangle over 5 meters, and again with a height of 15 kilonewton per meter. So those shapes, the area of each shape gives me the equivalent force for that distributed load. That equivalent force sits at the centroid of each shape. So for a triangle, it's going to be 1/3 of the length and 2/3 of the length, depending what side you're looking for. And for a rectangle, it's going to be half and half. So half the length and half the length. Now that we've clarified that, let us create a free body diagram and find the reactions. Starting off with point A, I see that I've got a pin support, so I can replace that support with 2 reaction forces, AY and AX. And at B, I've got a roller support, so I need to replace that support with a force of BY. Start off with sum of forces in the x direction equals 0, with this being my positive direction. And I can see here that I only have AX in the x direction, nothing else, so AX equals 0. Moving on to forces in Y, with this being my positive Y direction, I've got AY plus BY in the positive Y direction. And then I have the force from the triangular distributed load and the UDL. The forces, as we said, are the area, so minus 15 times 4 divided by 2. That is the force, and it's also the area of that triangle, and also minus 15 times 5, which is the force and also the area of the rectangle. And these have to equal 0. If I calculate that, I find that AY plus BY has to equal 105. Moving on to the sum of moments around A equals 0. So for this one, let's start off with the reaction forces. So AY and AX, they pass through A, they're not going to contribute to moment, but BY does contribute to moment. And that, as we've explained in previous examples, is going to be a positive moment. You can use the right-hand rule, or you can use a piece of paper, or you can use the idea you're travelling in the direction of the force and you need to make a U-turn to point A, which gives me a counterclockwise direction, and that is a positive moment. So plus BY, and the distance here is 9. Let's move on to the rectangular force. Now, we've already calculated it, haven't we? So we know that the force is going to give me a negative moment, so minus 15 times 5. That is the force, which is also the area of the rectangle, and that needs to be times by the distance. Now, if I look at this drawing here, the centroid of this triangle is here, and so therefore the distance from here to point A is going to be this distance here, which is going to be 5 divided by 2, right? Half of that length to where the centroid is, and 4. So my distance here is 5 over 2 plus 4. That's the distance. The distributed load from the triangle also gives me a negative moment, so that is minus 15 times 4 divided by 2. That is the force, which is also the area of the triangle. And in this case, let's do it in another colour, the centroid is here. It's at 1/3. So the distance is going to be this distance here, and that is going to be 2/3 of the length, 4. So times 2/3 times 4. And all of that needs to equal 0. So if I calculate that, I get 9 BY equals 487.5. That is from the rectangle, plus 80 from the triangle. So 9 BY equals 567.5, and BY works out as 63.056 kilonewtons. And now that I have that, I can go back to this equation and say that AY if I reorganize it, equals 105 minus by. So that is 105 minus 63.056. So AY works out as 41.944 kilonewtons. And that's it. I've found all the reactions. But what I want to do now is a check. And to do this check, I'm going to do the moments around B. And before I do this, let's just remind ourselves of what we have. We have this triangular force and this rectangular force, and now we're looking for moments around this point here. So the centroid of this shape is in the middle here, the centroid of this shape is at a third. So this distance here is going to be half of 5, and this distance here is going to be a third this time of 4 plus 5 here. So with that in mind, let's quickly do our check. So you've got minus AY times 9, that's from the reaction force, plus 15 times 5, that is the force of the rectangle, times, as we said, 5 divided by 2, that's the distance, plus the force from the triangle, so 4 times 15 divided by 2, that's the force, also the area of the triangle, and now times its distance, right, which is going to be a third of the length 4 plus 5. And all that needs to equal 0. So we get 9AY, if I rearrange, equals 187.5 plus 190. So 9AY equals 377.5, and AY therefore equals 41.944 kilonewtons. And that is what we got last time. So I think we can conclude that we solved this correctly. What I want to do now is replace those forces with the actual values. So AX worked out as 0, AY worked out as 41.944 kilonewtons, and BY worked out as 63.056 kilonewtons. Units, everything worked out. We've got kilonewtons for both reaction forces, and also we can see that the reaction force at B is slightly bigger than the one at A. And that makes sense because more of the load is distributed closer to B. So we've checked, done a sense check, done an actual check with the moments around B, and also checked our units, which means that we have solved this correctly. So once again, we've seen that it doesn't really matter what shape your distributed load is, or if it's a combination of different distributed loads, you can divide them into shapes that you know, like a rectangular and a triangle, and you can solve them using the fact that you know that the force is the area of the shape, and the distance for the moment will depend on where the centroid of that shape is. So now that we've solved that, and we also know how to solve point loads, the options for structures is really endless. We'll solve some more next time. In the meanwhile, bye for now.